Hello? Alright. Let's see if I got the ability. Oh, I might have a small thing I'm fixing here. Give me a second. So I've got no blackboard thing here. Good morning, everyone. As you get audio and no video for a change, usually it's the other way around. Da 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 dum. Alright, that's working there. Let's make sure it's working there. I knew that would happen. Alright, you guys should see stuff now. I hope. Alright, so we're kind of in the crescendo. Where things are going to be wrapping up. In fact, most of what I talk about today wraps up the mathematics we'll be discussing. I'll definitely do an overview on Wednesday, and for Monday, try to find some way to, I don't know, maybe I'll try a Zoom meeting instead, just where everyone can talk. I'm not a big fan of this unidirectional thing on this, but having done the Zoom thing in other classes, I think this is a little bit better control, as long as people talk in the chat room. Like you guys are good with that. Not all classes are. That said, if anyone is having any issues with Pearson or anything, please let me know. I've got, I think, one or two here. Hold on. I'm going to lose sight of you for a second. As I look here, I do believe, let me see, that I have tried to apply an email to everyone with any of the questions I see coming through. And I had seen a question come through right over the weekend. I think it was from Tina, but I'm not sure if I replied to it or not yet, and that's what nope. Alright, yeah, you're good, Tina. Thanks for letting me know. I thought it was a question on a question, but we're good there. Alright, so I don't think I have any examples to do outside of the main, with the main, lost my words, the main things due in Pearson. Alright, sorry. Just making sure that I replied to anything, and I'm babbling. You definitely need an extra strong cup of coffee here. I have moved things to get my actual chalkboard working. Let's see. I'll just give you an overview of where Crazy Jeff is. And that definitely sounds much louder by the microphone here. Where'd you go? Where'd you guys go? Where'd you guys go? Here you are. So what happens when you move stuff around. The May the 4th is already beginning. About the and yeah. And so I have an actual chalkboard here now that is usable. I guess when it works. That was odd. That's not that one, that's me. Hello. And that's not me. it's not letting me choose the other one. Interesting. Alright. Oh well. See? And that's the top of my head. Alright. So, but I have physically moved everything around. And so what you're hearing me here is I normally turn to my right to start quoting things. And I have to turn to my left here. Definitely need more of this coffee. Alright. So, does anyone have any impending questions? Alright. Give you guys a second or two. And then I'm going to get started on this concept of multiplying polynomials. Okay, good. That's visible. Good. Oh, there it was. Is the final exam on Pearson? Yes, it is. Couldn't really think of another way of doing it with all of this, so. Alright. Well, looks like the kids outside are playing really well. Alright, so that was the question Janine asked was, is the final exam on Pearson? And I said, yes, it is. Now, yeah, I'm going to have to move things back around. This turning this way is not working. I'm all discombobulated. It's all this left-handedness. You're going to hear some things move. Alright, now I should feel at least half of my little stand with my notes. Alright. So Janine asked about the worksheet. They're for your own practice. Worksheets are for your own practice. This is what we would have done in class. And I think they're a little more focused than the homework can be in general. I mean, they're very much related to what the homework does. But I think they're focused. And I think they're a really good thing to do right after talking about a particular subject. But I'm not going to grade them. All right, multiplying polynomials. Right? And so a little bit of a recap here as I scroll my morning down. This is definitely good coffee. It's working. All right, so polynomials. Are named by their terms. They have multiple terms, and terms are things separated by an addition or subtraction, where I'm going to write one. We have a variable. We will tend to write it in descending powers, and some coefficient or number and constants. When the terms have the exact same variable and degree to the variable, we can combine them. And so, for example, I have a pq squared, a p squared q, and a pq squared. These have the same variable combination, exactly the same. So I can combine those two. I have 3 of them here and 3 of them here. This addition adds them together. And that's what we call combining like terms. Good. Yeah, I would say polynomials tend to be a bit weird. I think a lot of it has to do we don't have an idea of what the value or quantity is yet. And so we're trying to build an idea of what this overall pattern does. And so we have collected like terms. We can add and subtract polynomials now. Some terms that we're going to come back. We're going to have a monomial, which is just one of these terms. That's a monomial. That's a monomial. Even that's a monomial. These individual things are monomials. We'll have a binomial. So mono is one term. Binomial is two terms. That's a binomial. And a trinomial is three terms. Now, in all of these terms, these ideas, we have collected like terms. We've pulled together things that were identical, identically named. And so they have been simplified down. And the two operations we used with these were addition and subtraction. Now, because polynomials are already made up of additions and subtractions, when we add or subtract polynomials, we build a new polynomial by looking for the things that have the same name. Multiplication doesn't let us off that easily. Multiplication can get a bit odd, but it's also very useful. And I want to emphasize underneath all of this represents one quantity. If I know what x is, I get a number back out of this. If I know what x is, I get a single number out of this. And so these expressions represent a quantity. They can represent all the possible values of a quantity, or they could represent one value given some conditions. And so our job is to kind of look for the pattern in this and help it for both of those cases. If we know what x is, or we know what we know any of the limiting constraints on them. And so we're talking about the pattern over all things do. So the first thing we can multiply, and the first thing we're going to look at, is multiplying any polynomial by a monomial. So we're going to talk about, I'm just going to give a general form, some larger polynomial, we'll call it poly, multiplied by something outside, and in this case it's a monomial. And so the first type of multiplication we look at is a single term thing multiplied by any polynomial. It can be another monomial, it could be another polynomial. So let's start with a monomial by a monomial. Because this is the building block for all other multiplications. And so I'm going to take the monomial 3x squared. Hope we agree that's a monomial. I have a variable to a power and some coefficient in front of it. It only has one term, so it's a monomial. I want to multiply it by this monomial. Now, I'm going to, for right now, jump back into all those rules of multiplication that we had and go, hey, these parentheses don't matter in a multiplication. I can multiply these in any order I like. So I'm going to get rid of the grouping symbols because this is a series of multiplications. I can mentally think of it as this without the parentheses. Then and we call that with the associative property of multiplication. Then we have the commutative property of multiplication, which is the order of the multiplication. Doesn't matter. So I will put the numbers out front. It's busy outside today. Sorry about that. So 2 times 3 is 6. And we have the same base and the exponents. So a multiplication with the same base, I add the exponents. And I have multiplied the monomial. Of course, these steps here, I'm illustrating the rules. All right, I've got some extra steps going on. Steps are extra. Usually, because these rules are always going to be the same, what we do, let me show another one to show you how people tend to think of it. Yeah, I'll do this one. I'll change colors here to show it's a different problem. Now, I know that I can associate these together, and I know I can commute them so that I'm going to multiply the numbers together, then I'm going to multiply the terms with the same base together. So knowing that these rules will always be the same, I look at the number to the number. 5 times 2 is 10. And then in x cubed times x to the 4th, same base, I add the exponents. And that's usually how people multiply monomials. These rules that we've developed in the beginning still apply. We can recognize that the numbers will multiply together and the exponents with the same variable will add. And so that's how all those rules coalesce around that. All right, I'll show you one that has more than 2 terms for multiplying monomials. And again, this is our building block. Again, I'll change colors to show it's a different one. I'll scroll up a bit. So I can multiply 3 things together if I wanted to, because it works. The rules just are the same. That's a 10. I wrote crooked writer. All right, so again, the rules of multiplication tell me that all these associations don't matter. I can look at this as one big long line of multiplications, and I would arrange it so that I did all my numbers first. So -2 times -4 is +8, and +8 times 10 is 80. So I would have 80 up front. Then in the things with the same name, I would add the exponents. So I have 3 x's here. I have x to the 3rd here, x squared here, x, so that's 3, 2, 1. That's x to the 6th, right? 3 plus 2 is 5. 5 plus 1 is 6. Then I would add my exponents of my y's together. y1, y4 is y5. That's y to the 6th. And I get that as my answer. All right, sometimes we multiply monomials and we don't even know that it was set up to be a multiplication at first. This is a multiplication. This says that I am multiplying what is in the parentheses by itself 3 times. But if we remember, or we flip back in the book, or we use a reference, because this will help us, we can do this 2 ways. I'm going to do it the remember the rule way first, which said if I have something to a power where there were different bases inside of here, it was the same as if each base had that power rule applied to it. So this is the same as negative 3 to the third power. It's the same as p squared to the third power. It's the same as r to the third power. So negative 3 to the third, calculator time, 27. My rule of powers here says a power to a power multiplies. And so this is using my power rule to do this. Well, if I forgot my power rule, and I know some people that still do this, if it's, squares and cubes, it's not too bad. So they write out what it means to cube something. Right? Isn't that saying the same as I cubed it? Because I'm multiplying what's in the quantity 3 times. So negative 3 times negative 3 is positive 9. Positive 9 times negative 3 is negative 27. I have 2 p's, 4 p's, 6 p's. P to the 6th. And 1, 2, 3 exponents. So r cubed. And so our rules work for us. I just wanted to illustrate that our rules work. This is the bedrock of all multiplication, is when we multiply things, it comes down to multiplying monomials. Monomials work their way through any type of multiplication we do. Just like back when we were learning multiplication, we could think of it as being made up of multiple additions, and when we were learning powers, we could think of them as being made up as multiple multiplications. Polynomial multiplications, no matter how complex they end up being, in the middle of them all is monomial multiplication. And so to illustrate this, let's multiply a monomial by a polynomial. So I'm going to take a monomial by a polynomial. Monomial by polynomial. It's weird having microphones, and I have headphones on to hear my own voice because I know I get loud sometimes, and I don't want to overload, and I don't have a compressor hooked up to this yet to like peak limit. If I get I don't have a good rack unit compressor. I just have guitar pedal compressors right now. If I got a half decent compressor for all of this, I could probably be a little bit better. I wouldn't have to be worried about being too loud, but then I might go into my radio voice and be like, "Hello, welcome to mathematics." But I have found that the voice I hear in my head, and literally because I have headphones on, not because I'm hearing voices in my head again, right? We took care of that. It just rings, and you'll hear me do it. You affect your voice differently because of the way you're hearing it, and something about this makes this very sing-songy to me. And so occasionally, monomial by polynomial. I don't mean to be silly. I just am that in this way. I'm over it now. Thank you. Okay, here I'm going to take the polynomial 7s, and I'm going to multiply it by 10s squared minus 3. Notice we have an addition sign in here. Well, an addition subtraction. Remember my weird take on PEMDAS? Because it works. That's why it's weird. Is these things are the same thing. Right? We just have to take care of what the sign means. Alright, so we're going to use this idea that when I distributed something, what was out front multiplies to each term. So this 7s is going to multiply by each term. And I know a lot of people will start using arrows to do this on their first step. And it's not a bad way of keeping track of things. So the first multiplication is 7s gets multiplied by the first term. So I have 7s times 10s squared. I keep my sign here, right? I can think of this as 7s times -3. So I guess I'll write it in this order so that the sign stays with it. And that blue isn't showing up too well. Oh yeah, it pops there. Okay. It's the light back on me there. Notice these are two monomial multiplications, just like what we were just doing. So this binomial in here creates two monomial multiplications. And that's what I meant when everything kind of condenses down into some form of this. So 7 times 10 is 70, and s times s squared is s cubed, and -3 times 7 is -21s. And so that is the result of the monomial by the binomial. Notice a couple things here, and this is going to kind of be important. The binomial has two terms, and this multiplication does nothing to cancel or simplify terms. It can't. It can't make these terms simpler, and so this will have two terms. Let's look at a few more of these in bright yellow. That blue's not quite right for me. Yeah, I want to do the big nasty one, an example in the book. -2m cubed n squared minus times, and they're going to multiply it by a binomial. So I have this monomial, and I'm going to multiply it by a binomial. My binomial's first term is this. Oh no, it's a trinomial. Man, the book does not like us, does it? I heard the book talking the other day. It definitely said it didn't like me. Probably likes you guys. Just doesn't hang out with you enough. So I have a trinomial in here, and I have a monomial out here. So what I'm going to do is I'm going to color code. This monomial has to multiply by this. It has to multiply by this. And it has to multiply by this. So it multiplies its way through each term. And so we're going to look at those multiplications one by one. So for this multiplication for the red, that's better. The red multiplication, this is a monomial multiplying a monomial. So I multiply the numbers first. -2 times -6 is +12. I have m to the third and m to the third. It's going to give me m to the sixth because I add the exponents on multiplication of the same base. I have n squared and n to the fifth. So I add those exponents, and that gives me n to the seventh. I know this stuff looks weird. We're putting the form of this stuff together. We'll start making it give answers for us soon. Right now we're getting used to the rules of addition, subtraction, and multiplication for this stuff. Oh, I didn't mean to put a plus sign there. Sorry about that. I'm on the green bit here. All right. So I have multiplied my first term, my monomial, to the first term. That was the red arrow. Now I'm going to do the green arrow here. And that's going to be my monomial times the second term. And so I start with the numbers. -2 times -2 is -4. It gives me the sign. of what's going on. Wasn't it nice of it to give me the sign? And we say, hey, thank you, monomial multiplication. And then an m cubed times m to the first gives me m to the fourth. And n squared times n squared gives me n to the fourth. And I've completed the middle term. Now, this monomial multiplies by the last term. So negative 2 times, well, what's hanging out in front of there? Right, our invisible 1. So this is negative 2. M cubed times, there's no other m here. Well, I still have that m cubed originally. Then I have n squared times n to the first, which is n cubed. All right. And so this ends up being our answer. Remember, I'm focusing on the rules of multiplication and addition and subtraction with polynomials. We're going to make them do work for us soon. And underneath all of this, we just want to remember this represents something that once I know what m and n are, I will get a quantity back out. Until then, this pattern describes all possible answers. And that pattern obeys all the rules that we have used before. Because it obeys all the rules before, we can manipulate it like this. We can make it, instead of 3 terms that we would add together and then multiply by something, we would make it with 3 terms that we just add together. The idea of condensing these things down is when we do know the other part, it's an easier calculation for us. All right, and I'm going to show the last thing we're going to do with monomial multiplication, and then I'm going to move into, this phrase gets used a lot, the bread and butter, right? The thing that gets used the most. The bread and butter phrase is the bread and butter phrase of talking about bread and butter things. No, that's not right. I guess it's just a cliche. But one of the most things that happens the most is we multiply binomials by binomials, which creates trinomials, and mostly, if it's all in one variable. And that seems to be a majority of the formulae we end up doing that. For some very esoteric reasons that I will babble on about when more appropriate when doing the word problems. But the last thing I want to do with the monomials is the fact that, well, we can do more than one thing. So this is 7s cubed times the polynomial 2s squared plus 5s plus 4. All of that minus the monomial s squared times the polynomial s squared plus 6s minus 1. Now notice what happened here. I can kind of think of this whole thing as 2 parts. Kind of, sort of. Okay. I have this monomial times this polynomial, and whatever the result of that is, I'm going to subtract from it this monomial times this polynomial. So let's work on the purple side here. And I'm going to, this monomial goes into here. And it has to go to each term individually. So I'm going to keep a line for each term individually. Let's see, red, green, purple. Nope. And this term will go to here. and go through each term individually. Notice that leading term has to work its way through every term in the polynomial that it's being multiplied through. So I will start here with the 7s cubed times the minus 2s squared. So 7 times negative 2 is negative 14. S cubed times s squared, well, I'm multiplying the same base, so I add the exponents, is s to the 5th. And that's the first term taken care of. Second term, I have 7 times 5. Well, that's positive, so that's positive 35. And I have s cubed times s to the 1st, so that's s to the 4th. All right. And that has taken care of the middle term, the green in my green spot here. Now I'll do the last spot. So I have 7 times 4, that's positive 28. Oops, I didn't want red, I wanted blue. It's positive 28. And s cubed times 1 is s cubed. And so I have done my first terms here. Now here comes a nice thing that comes out by the consequence of letting us think of minus signs as I'm multiplying by a negative 1. I can think of this whole thing as a negative s squared. So that'll keep track of my signs when I distribute this. So on the red distribution, negative s squared times s squared. So negative 1 times a 1 gives me a negative. And s squared, we have the same base, so I add the exponents, s to the 4th. And that's the first term here taken care of. Second term, I have negative 1 times 6, that's negative 6. And I have s squared times s to the 1st, that's s cubed. And then I have negative 1, oops, that finishes my middle term. I have to go to my last term here, change colors. I have negative times the negative, that's going to be a positive. And s squared times 1 is s squared. Whew, that was a long, hot mess. But I'm not quite done. I can blend like terms. I'm going to use shapes. I'm going to do everything in yellow because I started in yellow, and I'm going to use shapes. So this is x to the 5th, so I'll make that a big rectangle. I don't have any other s to the 5ths, right? But this is s to the 4th, and I have 2 of those. And this is x cubed. I only have 1 of those. And then s squared, I only have 1 of those. So I don't have any more of these, so this stays out front, right? Bringing like terms together, there's only one thing that has s to the 5th in it. That's a 5th. Every now and again, I'll pull out a question in the book that uses s's, and I know I should avoid s's because they look like 5s. All right, so here I have 2 s to the 4th. So I have 35 of them minus 1 of them. So altogether, I have 34 s to the 4th. And then I only have the 28 s cubes. And 1s squared down on the end. And that's my simplified version. Now, think about it. If this came out as something you had to do, like if this was a calculation that gave you the reaction time of something you were administrating times the amount of time you had, and this was the symptom time minus the amount of time you had, and this variable mattered, and this relationship mattered, and you calculated the amount of time you needed everything to work in, putting that number into here, adding all of them up, multiplying by this, then doing the same thing over here, there's many steps to do. this has reduced the amount of calculations that you need to do. Simplifying these patterns. Did I forget a 6x cubed? Did I forget a 6x cubed? Yes, I did, Janine. Thank you. I didn't even put a triangle under it. Janine for the win. So 28 minus 6x cubed. I don't know. Green blindness or something. So let me fix that. Thank you, Janine. Keeping me awake and alive. So 28 minus 6 is 22. Nice. So Janine pointed out to me that I forgot my 6s cubed. I took care of it. All right, that's my Hendrix quote for the day, as I missed my 6s. All right, so these rules, because they come from the rules of numbers, are valid. We're doing things that match all the things we've done with real numbers. We're able to propagate them through these more complex things. And yes, we're learning how to manipulate something when we don't know the values underneath. But what I want to stress is, if this is something you would know S for, and you wanted to plug it in, this would be the easier way to do it. And that's what's part of this is writing these things in the simplest form, so that when you find the variable, when you find the thing you've measured, the calculation isn't mind-numbingly crushing. It also, there are some patterns that are going to come out that we will see repeated, that when we get them into simplest form, our ability to recognize things will be enhanced. All right, so we've beaten the monomials. Let's look at two binomials times each other, and I'm going to do this. Remember, multiplication has this idea that a times b plus c equals ab plus a times c. So if I create a ugly binomial here, and I'm actually just going to use an example in the book, 3x plus 1, I'm sorry, that's a binomial, times another binomial, 5x minus 2. This whole thing gets multiplied to each term. All right. And so I'm going to write it out the long way. We will find a way of simplifying this, but I want to show you where everything comes from. You know I have that curse, right? Where I want to show where everything comes from. So the first multiplication would be, if I'm saying this 3x plus 1 is a, then I have 3x plus 1 times the first term, 5x. And then I'm going to bring this negative 2 out front. I'm going to have 3x plus 1 times negative 2, minus 2 times 3x plus 1. So I've taken this front part and I've multiplied it by each of the inner terms. Right? Well, I can repeat this again. This 5x can now be multiplied by, I'll change my colors here to red. This 5x goes into the first term, and it goes into the second term. Just like this negative 2 is going to go into the first term and into the second term. So up front, I can have 5x times 3x plus 1 times 5x. I'll just write those together. And then this is going to be minus 2 times 3x and minus 2 times 1. So notice it happens twice. And I'm going to finish this problem off because I want to get to the point, but show you this comes from a place. 15x squared plus 5x minus 6x minus 2. All right, I did this multiplication, added the powers, did this multiplication, did this multiplication. Notice these two terms in the middle have the same same name, so plus 5 and negative 6, and I'm not forgetting the negative 6 this time. Minus x minus 2. And I get a trinomial. And so mathematicians have had to do this a lot. Uh-oh, question. All right. So let me see. Oh, Tina got lost a little bit in here. It is a losing process, and I kind of rushed in the middle here because I want to get to the punchline. So we have this rule of distribution, that if I have something multiplying things added together, that multiplication can go to each term in the addition. So I took this thing outside, this whole thing in parentheses, and I multiplied it by each term. The 3x plus 1 times the 5x. The 3x plus 1 times the negative 2. That was my first step. But all over again, I have a 5x that can be distributed to everything inside the 3x plus 1. And so I have 5x times 3x, that gives me the first term, and 5x times 1 gives me the second term. And it also happens to the other part here. Because this whole thing in its own right was a binomial, when I multiplied it into each term, I was able to multiply it again. First line. Tina, do you mean the A, B, C? All right, so Tina's lost. I'm running back through it. This is a losing process, right? We're going to try to simplify it. The distributing and then distributing again and distributing again is the rule underneath it that makes everything work. The problem is there's lots of things to keep track of, and there's a pattern underneath all of this that we're going to simplify it to. So that feeling of lost is natural. Mathematicians had that, and they found a way out of it. And so I then collect like terms. So after we multiply these together, we multiply these together, we get these multiplications. So this is our given problem. I'm treating this as my A term. I distribute it to each term inside. So if this was my A, this would be A times B. This would be A times C. But these things, again, can be distributed. So the 5x goes to the first term here, and the 5x goes to the 1 here. The negative 2 goes to the 3x, and the negative 2 goes to the 1. I do those multiplications and create a trinomial. Well, something unique happens here. And what mathematicians found out, and we're going to get this thing called FOIL. There's a pattern underlying all of this that ends up being, notice this 5x multiplied through both terms in the 3x plus 1. And this negative 2 multiplied both terms in the 3x plus 1. So this bit ended up multiplying to this thing and this thing. This bit ended up multiplying by this thing and this thing. And so because each term got multiplied by each term in here, they didn't have to break it down anymore. And what they did is, in the case of a binomial times a binomial, this is only for that, they did this thing called FOIL, which is firsts, outers, inners, and lasts. Firsts, outers, inners, and lasts. So let me give another one to look at how this works with. Actually, I'm going to use the same one because I made that one confusing. Let's deconfuse it, which is what was the point. So let's see, I have 3x plus 1 times 5x minus 2. Now, FOIL says multiply your firsts together, so I'll do that in purple. There's my firsts. So 3x times 5x is 15, because 3 times 5 is 15, and x times x is x squared. So that's my firsts. Now I'm going to do my outers. So this is the outer one of this one, and that's the outer one of that one. So outers are going to come around here. And I'm going to have 3x times negative 2. So negative 2 times 3 is negative 6x. So I did my firsts. So check. Did my outers. Check. Now I'm going to do my inners. And so these are on the inside of this whole big thing. So these are my inners. And I have 5x times 1, or plus 5x. And then my lasts, well, this is the last one and this is the last one. So I'll get 1 times negative 2, or negative 2. My like terms are in the middle here. That gives me a negative x. And notice I got to the same result in relatively less steps. What we have to remember is this: I multiply the first times the firsts, my outer times the outers, my inners times the inners, and my last times the last. There is a pattern. If my binomial is some variable, so I'm just going to A some variable plus a constant times some other number times the same variable plus a different constant, right? So that's the form of this. And notice I had some variable, my variable is x, right? These were the same order binomial. So these things are of the same type, which is actually very common. Notice what happens here. You get these middle terms that reduce down to this. The outer terms determine the constant on the end. And the first terms determine this leading part. And so you'll hear a lot of times we'll talk about the middle terms. These are what the middle terms mean. The middle terms are the things that come to the middle, and the like terms that you have to gather together. And this pattern is the pattern of binomial multiplication. So let me grab another one. X plus 4 times 7x plus 2. So I'm going to remember to use FOIL. And so I start with my firsts. And I'm not going to draw arrows here right now. I'm going to use a verbal reminder for this. I leave it up to you to do that. I have never been an arrow person, mainly because I have horrible handwriting and the arrows got in the way of me seeing things. I have some people they'll write the FOIL down, and then they'll write each multiplication out, and they'll bring those things together. Other people do this on graph paper. You can do it as a grid. You can have x, 4, 7, x, and 2, and if you make a grid out of that, 7x times x gives you 7x squared, and they'll multiply everything in the grid and put it together. They're all the same way of what part of mathematics they call bookkeeping, keeping track of the things you do. I'm not a stickler that you have to do it, your bookkeeping, one way. In fact, I'll show you different ways of bookkeeping if I'm comfortable with them and I can explain them. But we need to keep track of what we do. And FOIL has been beaten into my head, and some of the other things that come out of this multiplication. So I when I see things like this, I go, what are my firsts? Here's my firsts. 7x times x is 7x squared. What are my outers? X times 2 is 2x. What are my inners? 4 times 7x, right? My inners. 4 times 7x is 28x. And then my lasts, 4 times 2 is 8. I know I'll be getting middle terms. So I know I have one more step, which is to add those middle terms. And that's the pattern we get out of these over and over and over and over again. I would, on the worksheet for this, practice these so that you get used to the pattern and you get used to the bookkeeping. I'm preparing for a class in next spring on ordinary differential equations, which is kind of the top level math class on the way out into more generalized math. It's kind of like the end of the calculus regime, and from there you get into your abstract algebras and other oddities. But in it, I was watching a lecture on MIT, and they were doing these because these type of equations drive even the higher upper end mathematics. This type of pattern repeats itself at many different levels. And the professor was saying, well, you know how to do this. It's FOIL. You should be comfortable because you know this pattern is going to repeat, that when I do the 2 times x and the 4 times 7, I should be doing this addition in my head. And I'm sitting here yelling at the professor going, it's okay to write that down, right? That's bookkeeping. And so there's parts of mathematics are bookkeeping, and there's parts of the pattern. And so the pattern is, I have these two binomials. If I have two binomials, then I'm multiplying them. They have one variable, or at least the variable terms are the same between the binomial parts. They're going to collect a middle term, and I'm going to get a trinomial out of it. And that's actually a very, very important pattern in mathematics. It is really the basis of, I would say, 60-70% of a college level algebra course, like the functions course here. It is this trinomial pattern that comes from binomial factors. All right, I'm going to do one more. And this is something that I suggest practicing, and I'm going to show you all polynomial multiplication, no matter what the polynomial is, be it binomial times a trinomial, a quinnomial times a quadnomial. You name it, you throw it all together, there's a way out of it. It even works for what we're doing right now, though it is I don't want to say messier, but it's a bookkeeping thing. It's all bookkeeping. The pattern's the same. In the end, we're multiplying monomials together. It's how we keep track of the monomials that we multiplied that's really the pain. So I'm going to say out loud, I have a binomial times a binomial. And I don't even think I say that anymore. I don't think the word binomial comes up that often in my lexicon, but I have a thing of 2 multiplied by a thing of 2. Like this doesn't even have a name in my head anymore. It's a pattern. The variables are the same. So I multiply the first times the first. 8x times 2x is 16x squared, because the x times the x gives me the x squared. My outer is 8x times negative 1, which is negative 8x. My inner is negative 3 times 2x, which is negative 6x. And my last is negative 3 times negative 1, which is plus 3. I should be looking for middle terms that have the same variable, because this pattern, this binomial times this binomial, is usually going to give me something like that. And negative 8 minus 6 is negative 14x plus 3. And that is a binomial times a binomial. All right. There are some special multiplications from binomials that come up a lot, and they always give a pattern. I'm going to do the special products right now, and then I'm going to go back to the general ones. So I could have two somethings. I don't care what these somethings are right now. And I'm going to square them. So I have a binomial with an addition in it squared. So I'm going to write it out long form here. Remember, what we're going to do is we're going to get a pattern out of this that always works. So my firsts, I have a times a, which is a squared. My outers is a times b. And my inners is a, or b times a, but I could write that as a times b. Right? Because the order of my multiplication doesn't matter. So there's my firsts, my outers, my inners, and my last is b times b, which is b squared. I have these middle terms that are the same. And how many of them do I have? Well, I have two of them. And so if I have a binomial squared, it's always going to give me that as its answer. So for example, if I have 3x plus 4 squared, I could write 3x plus 4, 3x plus 4, and I could FOIL it, or I could look at this pattern here. If this is a, and this is b, then an a squared is 3x squared plus 2 times 3x times 4, right? A, b, plus 4 squared. So 3x squared is 9x squared. 2 times 4 is 8, times 3 is 24x, plus 16. And this formula, people tend to memorize. I have never told people to memorize this. I've said, if you see this and you don't remember this, you can always rewrite it like this. And what happens is if you continue down a math track where these keep popping up a lot, this happens commonly enough. You start memorizing this pattern. It has a friend. If I square a minus b, this process repeats itself, and only one thing changes. The positive sign here changes to a negative sign. If you don't trust me on this, this is something that I say, hey, take this, work it out. Do what I did here. Do a minus b times a minus b. You'll find that you'll get a negative sign on your middle terms only, because the squaring in the front will make everything positive, and the negative b times negative b will still be a positive b squared. But I'll leave that up to you. If you doubt that, try that. Only one other one of these special ones I wanted to show you. So notice what I'm doing. I'm taking a binomial and I'm squaring it, and I'm looking at the difference between if it has a positive or a negative sign in it. The last one is a really neat one that I just ran out of paper for. Okay. Scrolly. Ooh, that hurts the eyes. Alright. I'm going to edit this and do the last one. Da 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 da. There we go. If I have a binomial and its friend, but the sign is different, and these end up getting special names. A plus B and A minus B are called conjugate pairs. And they're a really important trick when dealing with certain types of numbers. And so if you have the same thing, but you differ the sign in the middle, a neat pattern comes out. I'll show you this pattern. Again, this is probably the more useful of the two. So I do my firsts, which is going to be A times A. So the firsts are A squared. Then I'm going to do my outers. A times negative B is minus AB. Then I'm going to do my inners. Positive B times positive A, that's positive AB. And I'm going to do my lasts. A negative times a positive is a negative, and it's B times B, which is B squared. Notice I have a negative AB and a positive AB. They cancel each other out. And this ends up being called the difference of squares. And it is surprising how many times in reality a difference of squares pops up. The conjugate pairing is something that tends to happen in dynamical systems quite naturally. And so this pattern itself comes up a lot. And that's kind of all the weird things we see in multiplication. Notice any one of these special things I did, what they call special products in the book, I could do using the FOIL method. So if we FOIL, or some variation of FOIL, and keep our bookkeeping good, we're okay. We don't have to memorize these. We'll get back to it. All right, the last thing I'm going to show you is I'm going to throw FOIL out the door. I'm going to throw everything out the door because it's a sunny day. And I'm going to look at a large polynomial multiplication. A good example, a polynomial by any polynomial. So, yeah. I'll do x squared plus 3x minus 1 times x plus 2. Now, I can't do the FOIL thing I did because this is not a binomial. So I could take this whole thing and distribute it to each term. So I could have x squared times x plus 2. I could have 3x times x plus 2. I could have negative 1 times x plus 2. And then I could distribute each term through there. Well, a thing comes out of that. Remember when I did the FOIL, I said each part in here got multiplied by each part in the binomial. The same thing happens here. If I were to distribute this to the x squared term, then the x squared would have to distribute through here and get multiplied by each one of these. If I were to distribute this into here, I would get 3x times x plus 2, and the 3x plus 2 would have to work its way through each thing in there. Notice the each thing is getting multiplied, the each thing is getting multiplied. And so what we end up doing is we go, okay, x squared is going to have to be multiplied by both of these things. So I'm going to make my x squares red, make my 3x's green, and I'm going to make my negative 1's blue. Okay, RGB. So that we can watch them distribute. So x squared gets multiplied by each thing in here. So x squared times x is x cubed. And x squared times 2 is positive 2x squared. And I have now made sure that x squared got multiplied by each thing in here. So I'm done with the x squared terms. I'm going to move on to the green 3x terms. So 3x times x is plus 3x squared. And 3x times 2 is plus 6x. I have finished the 3x, and now I'm on the negative 1. So negative 1 times x is negative x, and negative 1 times 2 is negative 2. And I'll collect like terms. So I've only got 1x cubed, so that hangs out front. I've got 2x squared and 3x squared, so all together I have 5x squareds. I have a 6x, I remembered my 6. I have 6x minus x, so that's plus 5x. And I've only got one constant, negative 2. So whenever we have any polynomial times any polynomial, we can just pick one. Pick one and say, okay, each of your terms, I'm going to multiply by each term in here. So I picked x squared and I multiplied it by everything in here. And that gave me this set of stuff. And then said 3x, I'm going to multiply everything by here. That gave me this set of stuff. And I said negative 1, I'm going to multiply by everything here. That gave me this set of stuff. And I had taken care of everything. And this will work no matter how huge and ugly the polynomial is. I have a trinomial times a trinomial. I could have a quinnomial times a quinnomial. And I take one of them. And I take each term and multiply it by every term in the other one. And I'm going to do one more of these monsters. So again, I'm going to go to yellow. And I'm going to do, so I have 3t squared minus 2t plus 1. And I'm going to multiply that by 5t cubed minus 4t squared plus t plus 1. Make this as ugly as possible. So I'm going to pick one of them that I'm going to use to keep track of my terms. And I usually pick the first one. And I'm going to do the RGB thing again. Those terms are going to be red, those terms are going to be green, and these terms are going to be blue. And I need to take this thing and multiply it by each one of these. I'm going to take this thing and multiply it by each one of these. I'm going to need to take this thing and multiply it by each one of these. And then I collect my like terms. And so you just need to take one of your polynomials and use it to keep track. So 3t squared times 5t cubed. 3 times 5 is 15. And t squared times t cubed is t to the 5th, because I add my what are those things called now? Powers. And so that got me through the first one here. So I'll just put a little red tick there. 3t squared times negative 4t squared. Negative 4 times 3 is negative 12. T squared times t squared is, add my powers, t to the 4th. Now 3t squared times t, well, 3 times 1 is 3, and t squared times t is t cubed. And 3t squared times 1, anything times 1 is itself. Whew. Well, that was my red ones. I'll now do my green ones. And I'm actually going to come down a line for the green ones. So, whew, that was a while. I still got to do this 2 more times. So negative 2t times 5t cubed, right? Because I've finished all the red ones. I'm on the green ones now. And this has to multiply through each thing in here. Just keep my tick marks. So negative 2t times 5t cubed. Negative 2 times 5 is negative 10. And t times t cubed is t to the fourth. Right? Negative 2t times negative 4t squared, and negative 2 times a negative 4 is a positive 8. And t times t squared is t cubed. Negative 2t times t, that's a negative 2, and t times t is t squared. And negative 2t times 1, anything times 1 is itself. Okay, got the green ones. Now I'm on the blues. So 1 times 5t cubed, well, anything times 1 is itself. So that's positive 5t cubed. 1 times negative 4t squared. Hey, that's 4t squared. I like ones. Ones are nice. 1 times t is t, and 1 times 1 is 1. And I did a trick, the book recommends this, is lining things up by their powers. So when I collect like terms, I have 15t to the fifth out here. I have 12t to the fourth, which is negative, and negative 10t to the fourth, so that's negative 22t to the fourth. I have 3t cubed and 8t cubed, that's 11t cubed, plus 5t cubed, that's 16t cubed. For some reason I'm thinking like ice cubed and iced tea, right? T cubed, iced tea, yeah, I don't know. It's been my musicals. I'll behave. 3t squared minus 2t squared is t squared minus 4. That's minus 3t squared. And a positive and a negative gives me negative t plus 1. And that's my polynomial. I'm not going to throw anything that's this big of a multiplication at you, but I just need you to be aware that you can focus on it term by term, as long as each term here gets multiplied by every term there. And then you add your results together. And that's what FOIL did. Just the pattern in FOIL, because it's a 2 by 2, is a little easier to condense. These larger things, the larger the polynomial, the bigger it gets. And I want to stress the importance is we haven't done anything with these patterns yet, but this t means something to you. It's something you're going to measure. And if you had two measurements that you have to multiply together, doing this calculation than doing this calculation, multiplying them together, this is still easier on the calculator. And that's why we use these techniques. But it's okay. You know, Wednesday, we're gonna do the opposite. We're going to factor, right? And so we're going to start here and end up here. Because everything we do in mathematics is reversible, and we want to go backwards or forwards. And the going backwards in this is actually an extremely helpful thing. All right, that's everything I have for today. I'll send an email out. A couple people I know are saying about times on things or whatnot. Email me if you think you're going to need more time. I have to have the grades in by May 13th, which is why there's a May 11th deadline and everything. I can extend that if there's paperwork involved. And so if you are transferring out of here or graduating this semester, I don't want to extend it. Everything needs to be in on the 13th, and we have to work towards that. But if you're staying here and you need more time, then we should probably get the paperwork out. If you're comfortable with where you're at, doing okay, and you want to do the May 13th deadline, that's fine. You don't need to let me know anything. Here's the deal. It's easier for me if we get out of here at May 13th. I'm not really all about being easier for me. I'm what's ever best for you. But if you're not doing horribly, right, I would say we just try to wrap up. Remember, you don't need every piece of homework done. The homework's for you to practice. I'm worried more about the exams. So if you're worried about time on anything, send me an email and we'll have a conversation. In fact, I think all of today and tonight is going to be me replying to emails across my classes with things like this. And I understand it, right? Like, this is not normal. This is not how things were structured to work. There's no way I'm holding a normalcy expectation on anything, but I need to hear from people first. All right. Be well. I know this stuff is weird. Practice the worksheet on it. This is, once you start doing that pattern, that foil, you start doing it by hand a few hundred, 6,000 times, the 8 billion pieces of homework I did, it does start becoming second nature. And then we can start using it. And that's going to be the focus on the last class here. Bye, guys.